Let's begin our next discussion now on vectors. In this discussion we're going to begin talking about multiplication with vectors, and there's going to be three different kinds. First off, there's going to be multiplication with a scalar quantity. Remember, a scalar now has a magnitude but not a direction. So let's assume I have a vector A, and maybe this is walking 10 meters at an angle here with respect to the horizontal of 45 degrees. Well, let's further assume that I do that 3 times. I walk 10 meters at 45 degrees. I walk another 10 meters at the same angle of 45 degrees. And I walk another 10 meters at the same angle of 45 degrees. So this is the same vector. We'll call that vector R. This is R, and this is R. They're all vector R. And so in the end, I've walked 30 meters at an angle of 45 degrees. But that distance and direction is a vector sum of R plus R plus R. But that's nothing more than 3 times R. Now this number right here is a scalar quantity. It just has magnitude of 3. So I can always take a vector and multiply it by a scalar quantity. And when I do that, I get another vector in the same direction but with a different size. Unless, of course, I multiply it by 1, then it's the same size. So I can take any vector A and multiply it by a scalar quantity I'll call K. And this will give me a vector that has the same direction as A. So with the same direction as vector A, but a magnitude of K times A. Notice this A doesn't have the vector sign over it, so that's K, the scalar out in front, times the magnitude of A. So the magnitude of Ka is K times bigger than A. So in this case that we did right here, the magnitude is 3 times bigger than R. Now that scalar quantity can be an irrational number, so I could have a vector Q and multiply it by pi, and that would be a vector in the same direction as Q, and 3.14 times the magnitude of Q. I can also have a scalar quantity of, say, negative 2 times z, where z is a vector. And what that means is, for example, if z is off in this direction, if that's vector z, then negative 2 times vector z would be there and there, or this whole distance. So that would be negative 2 times vector z. So it has a magnitude of 2 times vector z, but in the opposite direction. So if z were equal to, say, 5 meters per second at an angle of 120 degrees, then negative 2 times z would have a magnitude of 10 meters per second, twice as big, but in the opposite direction. Now that's not negative 120. So if this is my Cartesian axis, 120 is off in this direction, so I have 90 plus 30, and this is going to be then 30 degrees here. So this is 30 degrees and 90 degrees, and that means this is 60 degrees. But that's in the clockwise direction, so that must be negative. So 10 meters per second at negative 60 degrees. So it's at 180 degrees if you multiply by a negative number. Or you could add 180 degrees. So I could say that negative 2z was equal to 10 meters per second at an angle of 300 degrees. And so that 300 degrees would be all the way around there. And so your 60 degrees, which is exactly what we have here, shy of the full circle. So that's how you multiply a vector quantity by a scalar quantity. Now, that scalar quantity might have units. So very common, we're going to talk about forces later on, and we'll talk about weight. And weight is equal to a vector quantity, and it's equivalent to mass, which is a scalar quantity, times the acceleration due to gravity, which is a vector quantity. And so perhaps I'm talking about a mass of 10 kilograms, and then the acceleration due to gravity is minus 9.8 meters per second squared, and that's always down, so generally that's the j direction. Not always, but we'll talk about that later on in the courses. So minus 9.8 meters per second squared in the j direction. And so this would equal a weight of minus 98 kilograms times meters per second squared in the j hat direction. We'll talk all about those units and what acceleration is in a later chapter. So the second kind of product we can have is a dot product. Now, dot product is often referred to as a scalar product. Now, this is not to be confused with scalar multiplication. The scalar product is given that name because the dot product is the product of two vectors. But when we're done with the dot product, we're going to end up with a scalar quantity. So let's assume I have two vectors, A, and this might be A sub x in the I direction plus A sub y in the j direction, and another vector B, and that might be B sub x, the x component of B, in the I direction, plus the y component of B in the j direction. So there's my two vectors. And so if I take vector A dotted with vector B, and we'll always use that dot notation to represent the dot product or the scalar product, then this is equal to A sub x times I hat plus A sub y times j hat dotted with B sub x times I hat plus B sub y times j hat. And the way we do this is we take the x components and we multiply them together. So that's A sub x times B sub x plus A sub y times B sub y. Now notice there's no I in here. Okay, there's the x terms, but there's no I hat. Here's the y terms. There's no j hat. These quantities are very specifically the magnitude of A sub x times the magnitude of B sub x. There's no vector here. And so when I'm done, this is a number and this is a number, and I'm going to add those numbers together. So here's an example. Let's say that A is equal to 5i plus 7j, and B is equal to negative 2i plus 4j. Then A dotted with B is equal to A sub x, but that's 5, times B sub x, which is negative 2, plus A sub y, which is 7, times B sub y, which is 4. So this is negative 10 plus 28, and this would be negative 18. So A dot B is negative 18. Not I, not J. There's no direction there. It's just a magnitude, just a scalar quantity. And I could do the same thing in 3 dimensions if I had M as a vector, and that would be M sub x in the I plus M sub y in the j plus M sub z in the k direction. And maybe I have a vector N, that would be N sub x in the I plus N sub y in the j plus N sub z in the k. If I took the dot product of M dot N, then I would get M sub x N sub x plus M sub y N sub y plus M sub z N sub z. And these, there's no I, j's, and k's there. These are just numbers, and I'm going to get a final number in the end. Now in addition, if I have two vectors and I'm doing their dot product, let's assume I have a vector s and another vector t. S and t are both at some angle from the positive x-axis. They both have some magnitude. So let me just say the magnitude of t, just write as t with no vector sign over it. The magnitude of s, I will write as s with no vector sign over it. Then I'm going to tell you that there's some angle in between s and t. I'm going to call that angle alpha for now. Then the dot product of s times t is equal to the magnitude of s times the magnitude of t times the cosine of the angle in between those two vectors. This is a good example of where polar form might come in really handy. So for example, let's say that s is equal to 14 at an angle of 45 degrees, and t is equal to 10 at an angle of 80 degrees. Then I can say that s dot t is equal to 14 times 10 times the cosine of 80 degrees minus 45 degrees. And so this would be 140 times the cosine of 35 degrees. And so my numeric value here would be 114.68 No degrees, there's no units that have been given there. I might write S this way. 14 at an angle of 45 degrees, that's equal to 14 cosine 45 degrees in the I direction plus 14 sine 45 degrees in the j hat direction. T is equal to 10 at an angle of 80 degrees, so that's 10 cosine 80 degrees in the I hat direction plus 10 sine 80 degrees in the j hat direction. So I might write this as 9.899 in the I direction plus 9.899 in the j direction. And I might write this as 1.736 in the I direction plus 9.848 in the j direction. Well, if I take 9.899 and I multiply that by 1.736, I get 17.184, 185 if I round that up. And if I take 9.899 and I multiply that by 9.848, I get 97.485. And if I add those two together, I get 114.67. The variation here being round off. There's no mistake or no small error. That's just the way that I've rounded off my numbers. If I were to pull out all of the digits of my calculator, I'd get the exact same thing. So you can see either way that I do a dot product, I'm going to get the same answer. Now notice a couple of things. First off, S dot T is equal to T dot S. So the dot product is commutative. And you can see that if we look back here, A dot B was A sub x times B sub x. B dot A would be B sub x times A sub x. No variation there. Same thing here with the y's. A sub y times B sub y, because these are not vectors, these are scalars. It's just regular multiplication. So A sub y times B sub y is the same as B sub y times A sub y. So it is commutative. The other thing you'll note is that if alpha is equal to 90 degrees, that's a very special case, the cosine of 90 degrees is equal to 0. So two vectors that are perpendicular will always have a dot product of 0. Okay, let me repeat that because it's very important. Two vectors that are perpendicular will always have a dot product of 0. And then if the two vectors are in the same direction, then I just get the cosine of 0 because they're in the same direction, and that would be 1. Another way to look at this, let's go back to S. I'm just going to draw this a little bigger now. And T. If I were to drop a component of T that was perpendicular to S, I might call this T perpendicular. And then here on this side is the component of T that is parallel to S. And here's the angle alpha in here. And so I can see that T parallel is equal to the magnitude of T, so that's just the size of this side, that's the hypotenuse, times the cosine of alpha. Or I might write it this way, the cosine of alpha equals T parallel over T. T parallel is the adjacent side, and the hypotenuse is T. And so that just rewrites in this direction, where T times cosine of alpha is T parallel. And so S dot T is equal to S times T times the cosine of alpha. And that's equal to S times T parallel. So sometimes I'll say S dot T is equal to the magnitude of S times the component of T parallel to S. The magnitude of S times the component of T parallel to S. Now I can do this in a similar fashion. I can write S dot T equal to S parallel times T. That is the component of S parallel to T times T. And on my diagram, I'm going to extend T out, and so I will drop a perpendicular, so this is 90 degrees. So right here is S parallel. So this is the component of S along or parallel to the vector T. And you can see the cosine of alpha is going to equal S parallel, that's the adjacent side over here, over the hypotenuse S. Then finally, the third vector product that we're going to talk about is a cross product. And this is in fact also referred to as a vector product. And the reason for that is very similar to the dot product. When I'm done with a cross product, I'm going to end up with a vector quantity. All right, now we might as well jump into 3 dimensions here. So let's assume that I have a vector p, and that's going to have an x component in the I direction, plus a y component in the j direction, plus a z component in the k hat direction. And I'm going to have a vector q, which is going to have an x component in the I direction, plus a y component in the j direction, plus a z component in the k hat direction. So p cross q then is going to be p sub y times q sub z minus p sub z times q sub y, all times I hat. So notice this is the x component, but these are y and z components, plus p sub z q sub x minus p sub x q sub z times j hat, so that's the y component, this is x and z, plus p sub x q sub y minus p sub y q sub x times k hat. So you'll notice that when I'm done with my cross product, this is a vector quantity. There's an I component, a j component, and a k component. So the product that we get with a cross product is a vector. Notice also, if I reverse q and p, I'm going to reverse these terms in every one of these. And that minus sign tells me that when I reverse the terms, I'm going to get a negative sign, or the opposite sign. So q cross p is not equal to p cross q. As a matter of fact, q cross p is equal to minus p cross q. Now, if you know anything about determinants, we can evaluate this using the determinant. So p cross q is equal to I, j, k, p sub x, p sub y, p sub z, q sub x, q sub y, q sub z. And that's all in the determinant. And the way you evaluate a determinant is you start off by taking, we're just going to use the upper left-hand corner. I'm going to start here, so there's I hat. And then I take away the row and the column that I hat is in, and actually that's the column and the row. And I'm left with p sub y, p sub z, q sub y, q sub z. So there's the I hat part. And I go to the j hat. Now the rule of determinants is if this is positive, this is negative, and this is positive. So I'm going to subtract j hat. I take out the row and the column that j hat is in. And I'm left with p sub x, p sub z, q sub x, q sub z. So I'm done with the j column. And then here's the k. I take out the column and the row that k is in, and that's positive, so plus k hat. And I'm left with p sub x. I'm left with this. P sub x, p sub y, q sub x, q sub y. And then if I have a 2 by 2 determinant, a, b, c, d, this is equal to a times d, so those two, minus the product of those two, which is b times c. You could say c times b if you like, but bc times c, b times c is the same as c times b. So coming from my previous page then, p cross q is equal to I hat. There's my determinant. So that's py times qz. So py times qz minus pz times qy minus j hat. And that's going to be px times qz. So px times qz minus pz times qx plus k hat. And so there's that. That's px times qy minus py times qx. And you'll notice this line is the same as this line. you'll see this is reversed, but there's a minus sign out in front on the next page. So notice pz times qx is the first term. Here pz times qx is the second term. So that makes it opposite in sign, but then there's that minus sign. So I always find it easier to remember the determinant. ijk, then the x component, y component, z component, then the x component, y component, z component of the second vector quantity. Now it turns out that the magnitude of p cross q, so the magnitude of this vector, equals the magnitude of p, so notice there's no vector sign there, times the magnitude of q times the sine of alpha, whereas in the dot product, alpha is the angle between p and q. And so if this is p and this is q, then here's alpha, that's a vector quantity, then the cross product is p, magnitude of p times the magnitude of q times the sine of alpha. And if we think about the parallel component that we used before, in this case we're going to look at the perpendicular component. So this is p perpendicular. The sine of alpha equals opposite p perpendicular over hypotenuse p. And so this is equal to p sine alpha q, which is the same as the component of p perpendicular to q times the magnitude of q. Let me repeat that. The component of p perpendicular to q times the magnitude of q. Or if I extend p out, I can drop a component of q perpendicular to p, then the sine of alpha in this case equals q perpendicular, the opposite side, over the hypotenuse. And so p cross q magnitude then is p q sine alpha, which is p times the component of q perpendicular to p. The other thing that's of interest is that whenever I take p crossed with q, I'm going to get another vector, and that vector, we call that mutually perpendicular to p and q, which means it's going to be into the board in this case, or into the screen. So that p cross q is a vector perpendicular to p and perpendicular to q. And as I draw two vectors in two dimensions, the only way I can do that is into the screen. The other thing to keep in mind here is that if alpha is equal to 0 degrees or 180 degrees, the sine of alpha is equal to 0. And so p cross q is equal to 0. And that makes sense because if p is in this direction and q is in that direction, there is no single vector. This is perpendicular to both of them. This is perpendicular to both of them. Something into the page is perpendicular to both of them. Something out of the page is perpendicular to both of them. And so there is no single vector perpendicular to both of them. And so there is no solution. And that's why we get a 0. So let's go to vectors in 3 dimensions. Now traditionally in math and physics, we're going to put x coming out of the board, y to the right, and z is up. Engineering is going to put x to the right, y up, and z out of the board. But we're going to do it the math and physics way. Let's assume I have some vector a. Then there's an angle between a and the z-axis. I'm going to refer to that as theta. And then I can drop a until it reaches the xy plane. So think of that as the floor. And then it's going to cast a shadow on the floor. And that shadow is going to have a length of rho and an angle with respect to the x-axis that I'm going to call phi. And so there's a z component of a right here, and the z component of a is equal to a times the cosine of theta. And then a times the sine of theta will equal this rho here. That's the component of a on the xy plane. And then there's an x component of rho, I'm going to call that rho sub x, which is also the x component of a. So a sub x equals rho times the cosine of phi, but rho is equal to a times the sine of theta, and then times the cosine of phi. In a similar fashion, a sub y is going to equal a sine theta sine phi. And so oftentimes in spherical coordinates, a will be equal to some length of a, and then there's an angle phi associated with a, and an angle theta associated with a. And we're going to work with this during a laboratory experience sometime in the future. In cylindrical coordinates, instead of worrying about theta, I'm going to worry about a rho, a phi, and a z, because all I care about is this rho as far as the xy plane goes, and then there's going to be some z component here.